Okay, good afternoon. I am Andrin. I'm from Stony Brook, and this is a recent work with my advisor on parallel multi-client ORAMs. So to begin with, I put a cartoon on the first slide because I don't think I have to try very hard to convince you that it's all about the clouds. We are using a lot of data storage, and the idea is every small cloud now wants to grow up and become like one of these big cloud providers you see on your right. And so this means that we are outsourcing a lot of our data, which includes both confidential information. And because there is such a lot of confidential information now outsourced to these clouds, we of course need to be worried about protecting this data. And protecting outsourced data could mean a lot of things. It has a lot of adversarial challenges. But as a first step, you could always encrypt your content before outsourcing to the cloud. And in many cases, this will actually work for you. But let's say you have ultra-sensitive data that you want to store on a cloud provider that you do not trust, then probably you need something more than encryption. And the reason is that even with encrypted data, a cloud provider will be able to observe all your access patterns, which means what items you're accessing, how often you're accessing them, and what kind of operations you're performing on them. And it turns out that leaking your access patterns can completely undermine the protection of encryption in several scenarios. So if you wanted to hide your access patterns, one solution you could use is an Oblivious RAM. And at the very high level, what an Oblivious RAM protocol allows a client to do is access items from an untrusted physical store without leaking to the storage adversary which items you're accessing and what kind of operations you're performing on them. So Dilbert here wants to access an item from the cloud, but Dilbert is really careful about security. So instead of just downloading the item, Dilbert uses an Oblivious RAM protocol, and now what the cloud sees is a bunch of random accesses which are not correlated to the item I. Okay, now before we move on, I want to discuss a little bit about an existing Oblivious RAM construction because this is an important building block for our construction. Okay, so the ORAM I want to talk about is path ORAM, and there are two parts of the storage in path ORAM. The client-side storage is on your left, and on the right you have the server-side storage, which includes a binary tree. Each node of the binary tree can hold a constant number of blocks, and logical blocks are placed along random paths in the binary tree. You need to maintain a lookup table. This could be on the client, and it's called the position map, or you can also store it on the server using more sophisticated techniques. So the way an access works is you simply download the contents along the path to which a particular block is mapped, and now you have this block in your client-side stash. Now, because you have read this block, the next time you read this block, you don't want it to be from the same path, otherwise you will be correlating these accesses. So what you do is you start by remapping this block to a new path, let's say V0, and then you write back the contents from your stash to the server, now ensuring that this block is along the new path. Subsequent work has also observed that instead of writing back to the same path that you read, you can also write back to a predetermined set of paths, and this is important. I'll revisit this point a little bit later. Okay, so for single client scenarios, path ORAM is great, it's really optimal, but let's see what happens in multi-client scenarios. First, let's say two clients want to access the same item from a path ORAM. Unfortunately, they will read the same path, and the server will now be able to correlate these accesses. So you're losing inter-client privacy. The second is, let's say a client is writing to one path, and there is another client reading from a different path. These paths will necessarily overlap at some point on the tree, and it will be difficult to guarantee consistency for all the nodes at this level or higher up in the tree. So you have challenges with correctness. Now, to get over this, there are two previous approaches. One is called an Oblivious Parallel RAM, or OPRAM, and the assumption in OPRAMs is that clients can coordinate and communicate with each other, and you can get over the security and the consistency problems. But the disadvantage here is, of course, that inter-client communication is rarely suitable for practical scenarios. Clients need to be aware and online, and this is not really possible in normal cloud deployment scenarios. The second approach is to eliminate the inter-client communication, but now introduce a trusted proxy in the middle. The first problem with this approach is it simply violates the ORAM trust model, where you have a set of trusted clients, and you have an untrusted server. If you really had a trusted proxy which had enough computational and network resources, why not use this as your server, and then you have a trusted server, and you do not need an ORAM anymore. Also, we see in our experiments that this proxy actually becomes a throughput bottleneck. So there is performance issues with introducing a proxy in the middle, and I'll talk about this more when I'm discussing experimental numbers. So in ConcurORAM, what we do is we design a parallel ORAM construction which does not require any kind of inter-client communication. We eliminate the proxy from the middle, so overall our throughput scales much better. And this is possible due to 3 key innovations. Parallel queries, which means that you can now execute multiple queries in parallel. Non-blocking evictions, which means that evictions do not need to block queries. And parallel evictions, which means we can now execute multiple evictions at a time. So I'll discuss all of these at a high level. So parallel queries, the idea is pretty simple. In addition to the server-side tree, you store a query log, which is simply a transaction log with all the ongoing query addresses, and a result log, which simply obliviously caches results, query results, before they can be put back on the tree. Now, the way an access works, so let's say a client wants to access a particular item from the tree. He first downloads the query log, checks if there is already an access for the same block. If not, the client appends the block address to this query log and writes back the query log. Then the client proceeds with the query, reading the path from the tree, and then once the result has been obtained, the client writes the result back to the result log. Now, let's say if there is another client that wants to query for the same item, she first reads the query log, she finds that there is an overlapping access for the same item. So what she does is she instead reads a random path from the tree, which is a fake query, and then when she wants the result, she finds it in the result log. Now, of course, you can understand there is going to be some amount of synchronization you require for this protocol, which requires some fine-grained locks, but that is actually quite small. Most of the expensive steps, which is reading and writing back to reading from the tree, can be done very fast and in parallel. So this is quite a good idea to parallelize the queries. The problem is, even when you have parallel queries, it's not really going to help you a lot in terms of tree-based ORAMs, because the most expensive step you have in a tree-based ORAM is the eviction. So while you're performing the eviction, if you block the queries, the gains that you will have from this parallelism is going to be limited. So one thing we can do here is we can introduce non-blocking evictions. Now, the challenge is evictions and queries will access the same data structures, unfortunately. So one insight we have in ConcurORAM is you can actually use separate trees for the evictions and the queries. So evictions will update a write-only tree, and queries will be satisfied from a data tree, and you will periodically sync between these 2 trees. Right? When you're syncing, you still need to block the queries. So what we do is we carefully analyze the eviction procedure, and we split it into 2 parts. So the most expensive parts of the eviction protocol are now performed as part of the processing, which involves most of the network communication. And then you have a very short commit phase where you sync all these contents from the write-only tree to the data tree. And this involves mostly reference swaps on the server side, or you have copies between server-side data structures, which does not require a lot of network communication. So with non-blocking evictions, we are doing better because now queries can be performed while you're also doing the eviction processing. But we have introduced a new problem by doing this, which is queries will be performed in the background, and so you will keep on generating results, but you can only perform 1 eviction at a time. So that means your queries will be query results will be generated at a much faster rate than what you can evict back to the tree. So one solution we have here is we can perform multiple evictions, but of course this is not easy because evictions will overlap at some level. Eviction paths will overlap at some point of the tree, and consistency is going to be a problem. So one insight here is I told you a little while before that you can select eviction paths deterministically. What this means is that you can also predict the overlaps between consecutive eviction paths. So for example, the first eviction is to this path, and you have the next eviction is deterministically is going to be to this other path. Then deterministically you know that these paths will overlap in this upper subtree. So all these accesses in this upper subtree can actually be performed with fine-grained locks, while the accesses to the rest of the path can be performed in parallel. And this actually turns out to be optimal because the way eviction paths are selected deterministically, 2 consecutive eviction paths are selected with minimum overlaps. So the height of this upper tree that you end up with is actually going to be optimal, and it's going to be log k plus 1. Okay? So the critical section you will actually have during your eviction is going to be small, so your evictions do not have to wait for a long time for each other. Now, with parallel evictions, we are doing even better, because now you can also write back queries faster to the tree, and you can evict to multiple paths in parallel. There are several other challenges that we have to address before we can make everything work. This includes how do we order the eviction commits now that we have defined critical sections? How do we store and privately query the results before they are returned back to the tree? How we are able to maintain the consistency of metadata, and of course fault tolerance, because now you have the clients do not really communicate and they're performing this eviction protocol in a collaborative way. But I'll encourage you to look at the paper for more details on this. Instead, what I'm going to talk about is the performance. So what kind of performance benefits do we really get from parallelizing the ORAM protocol? So the only ORAM that we should be actually comparing against is this ORAM from 2012 called PDORAM, which is another parallel ORAM that works without any kind of assumptions. However, PDORAM works on a slower base ORAM. It uses a hierarchical ORAM. So asymptotically, ConcurORAM is going to be faster. And that is the result you see here. So we are measuring the throughput, that is operations you can perform per second versus the number of clients. And of course, you can see that ConcurORAM throughput scales much better, almost by a factor of 8 to 10. But you might want to also use TauStore. So you might find this is a deployment scenario where you're OK with a trusted proxy. In this case also, you will, however, find that the ConcurORAM throughput will scale better. This is because in TauStore, you're actually limited by the network limitations of your proxy. So if you keep on increasing clients in the system, then you will saturate the proxy bandwidth very quickly. OK. The other number I want to talk about is query latency, which is the time that you require to complete one query. And again, comparing with PDORAM, we are doing better because we have a faster base ORAM. Now, you might want to compare with TauStore, in which case you will find that ConcurORAM is bounding the query times better because, again, the clients are not, when you add more clients to the system, it's not really affecting the query times of the other clients to a certain extent. But that is not really true in case of TauStore because adding more clients now is overburdening the proxy. OK, so I'm quite quick. OK, to summarize, ConcurORAM is the first tree-based parallel ORAM, which does not require any kind of inter-client communication, does not require any kind of trusted third party, so we do not have any assumptions. In this model, we are able to parallelize both the queries and the evictions. And as a result, we have really good throughput scaling. It's almost a 2 times overall throughput, better throughput than TauStore. OK, and before I end, I just want to take a little bit of your time to self-advertise. I'm on the job market. I build provably secure systems to address critical privacy challenges. And this, of course, includes the ORAM work, but that's not the end of the story. I also build plausible deniability mechanisms to hide your information from corrupt nation-state adversaries, and this is really critical in the environment of censorship and human rights abuses. I work on protecting integrity of cloud user data on untrusted cloud platforms. I worked on secure CPU architecture and secure virtualization for privacy-preserving computation, and I'm generally interested in other privacy problems like history-independent data structures and query authentication of databases. So with that, I'll conclude. I thank you for your time, and I'll be very happy to take questions.
Hi, Chris Fletcher from UIUC. Nice work. Did you consider using the partitioning framework for reducing contention on the ORAM trees presented at NDSS 2012?
No, not really. I have not looked into that, but that would be probably an interesting idea.
OK.
Yeah.
Hey, Gabe Kapchuk from Johns Hopkins. Great talk. If you go back a couple slides,
Sure.
I was having a little trouble interpreting the results. It seemed to say, one more slide back.
Yeah, sure.
Both megabytes per second and ops per second on the y-axis. So is it?
The title is a different title.
Yeah. So is that the number of operations that are going through per second, or the number of megabytes that?
This is operation per second. I apologize.
Okay.
Sorry.
Sorry.
Vincent Micheller, University of Florida. I'm curious, what kind of sequentialization guarantees do you have? Do you guarantee, for example, to always read the most up-to-date information?
Yes. So the challenge there is how do these evictions commit? So we have, and that's quite a non-trivial task. So first, we allow these evictions to commit asynchronously, which means that evictions don't have to wait for each other to commit, which is quite non-trivial. But what we ensure is you always find out the most updated version of the block while you're reading the result log or from the tree. So we do guarantee that
Okay,
consistency.
thank you.
Thank you.